We have defined power and energy in general for a two terminal element. Now, we will apply it to all the elements we know one by one and study their properties. Okay. First, we will consider the resistor. As usual, take voltage and current with the passive sign convention, and for any two terminal element, P of course is V times I. Okay, and each of these can be time dependent also. But now, for a resistor, the voltage is current times the resistance. Okay. So, this particular relationship is for the resistor, which can be written as IR times I, that is, this is the voltage, that is the current, which is I square R. Alternatively, it can be written as V times V by R. This is the voltage, that is the current, which will be V square by R. Okay. Now, of course, if voltage or current is dependent on time, then power will be varying with time, but the expressions will be the same. This is the power delivered to the resistor, which can also be written as V square divided by R. Okay. So, this is the expression for the power delivered to a resistor. Now, one thing we can notice is that because it involves the square of either the current or the voltage, and the voltage and currents themselves are real, the power delivered to the resistor is always positive. Okay. The resistor always absorbs power, right. So, that is very easily seen from this expression for power proportional to the square of the current or square of the voltage. The resistor always absorbs power, and where does it go? It gets dissipated in the form of heat. Okay. So, if you pass current through a resistor, it will heat up. Okay. So, it absorbs power, it actually dissipates it, and the power actually goes into heating up the resistor. In fact, that principle is used for many useful gadgets as well. If you have an electric stove, what happens is that you pass current through the coil, which is really a resistor of some sort. The resistance value has been adjusted, so that the amount of power heats it up to a certain extent, which is useful for whatever purpose, say cooking or something like that. Okay. Now, you consider energy delivered to the resistor over any time interval, it does not matter. Okay. From T1 to T2, it will be I square R dt, or T1 to T2 V square by R with respect to time, and this also obviously is always 0, because the power itself is always 0. So, a resistor always absorbs energy, it can never deliver any energy. Okay. Okay. So, something that can only absorb energy, but can never deliver a net energy, it cannot act as an energy source, such an element is known as a passive element. Okay. So, a passive element, either the power is always positive, which automatically implies that it always absorbs energy, it can never deliver it, okay, and such an element is a passive element. Okay. So, a resistor only absorbs power, which consequently means that it can only absorb energy, it can never generate energy and provide it to the rest of the circuit. Okay. Here of course, we are considering resistors with a positive value. Okay. A physical resistor always has a positive value. So, here I have to mention that we consider R more than 0. Okay. So, such an element is known as a passive element. We can also see graphically if I plot the IV characteristics of a resistor, this we have done earlier while discussing resistance. Now, whatever the value of the resistor, the curve is always a straight line with a positive slope. Again, I am considering the resistance to be more than 0. Okay. We do not consider negative resistances here, we consider physical resistors here, which have a positive resistance. So, now the characteristic is a straight line which passes through the origin. So, that means that it lies in the first quadrant and the third quadrant. And in the first quadrant, of course, both V and I are positive. So, the product is positive. So, that means that the power is greater than 0 as we have defined it, and the power we have defined is the power delivered to the resistor, power delivered to the element. Okay. This is the significance of the passive sign convention. Passive sign convention is such that if you take voltages and currents according to the passive sign convention and multiply it, the result will be positive if the element is absorbing power. Okay. Now, in the first quadrant, both the voltage and the current are positive. So, the power is more than 0, clearly the element is absorbing power, and in the third quadrant, the voltage is negative, the current is also negative, but V times I would be obviously positive. So, that means that again the element is absorbing power. Okay. So, a resistor is in the first and third quadrants. So, it always absorbs power. Here when I say absorbs power, we are talking about the element whose VI characteristics we are plotting. Now, conversely, if it happened to be in the second or fourth quadrants, it delivers power. Okay. So, if you happen to have a negative resistor, it will deliver power because the slope would be negative. Okay. But of course, such a resistor cannot be physically realized. You can realize them using active circuits, and that part is outside the scope of this course. Okay. Now, I will generalize here. Of course, the resistance has a straight line characteristics. Even if an element does not have a straight line characteristics, as long as it lies only in the first and third quadrants, which means that it has to necessarily pass through the origin, it will be a passive element. Okay, because it will only absorb power. So, let me draw one such example here. Okay. This element may be familiar to some of you. There is something called a diode, and its characteristic passes through the origin, and it looks something like this roughly. Okay. It is nonlinear. So, it is harder to analyze circuits with diodes, but one fact is certain, that because the characteristics lie only in the first and third quadrant, this also absorbs power. Okay. So, if you are in the first and third quadrants, it means that you absorb power, that is, we are referring to a passive mode of operation, and element which is only in first and third quadrants is necessarily a passive element. And if you are in the second or fourth quadrants, the element delivers power. So, it is active if it is operating in the second or fourth quadrants. Later we will see elements such as voltage source or current source, which can either deliver power or absorb power. Okay. So, from this part a couple of things should be clear. First of all, a resistor always absorbs power, consequently it always absorbs energy, it is a passive element. And we also discussed the characteristics and the implications on passivity. If you have IV characteristics in the first or third quadrants, then the element is passive. If it happens to be in the second or fourth quadrants, it can be negative. Later we will see elements which can be either passive or active. Depending on the quadrant in which it is operating, it could be either passive or active. Okay. Now, the units of power are, as you know, watts. Okay. For electrical power, 1 watt equals 1 volt times 1 ampere. Okay. The unit of energy is a joule, and 1 watt equals 1 joule per 1 second, or 1 joule is 1 watt times 1 second. Okay. Now, let us consider a simple case. We have a 1 kilo ohm resistor with 2 volts across it. By Ohm's law, we know that the current is 2 volt divided by 1 kilo ohm, which is 2 milliamp. So, the power dissipated in this when 2 volts is across the resistor is 2 volts times 2 milliamps, which is 4 milliwatts. Okay. Now, you can also calculate this as V square by R, which is 2 volt square divided by 1 kilo ohm, which is 4 10 to the minus 3 watts, which is 4 milliwatts. Obviously, we will get the same answer if you use I square R, which is the square of the current times the resistor. You have milliamp squared here, so this is 10 to the minus 6, this is 10 to the 3. So, we have again 4 times 10 to the minus 3 watts, which is 4 milliwatts. Okay. Obviously, all these should give the same answer because all those formulas are formulas for the same thing, the power dissipated in the resistor. Now, let us say this 2 volts is applied to the resistor for 500 seconds. Okay. So, the energy delivered in this 500 second interval is the power, which is 4 milliwatt, times the time, which is 500 seconds. We have applied a constant voltage, so we just have to multiply by the time interval, the power by the time interval. If the voltage were time varying, the power would be time varying, and you would have to integrate it over this time interval. This will turn out to be 2000 millijoules or 2 joules of energy. Okay. Very simple calculation, but as long as you know the voltage across a resistor or a current through a resistor, you should be able to calculate the power delivered to the resistor or energy delivered to the resistor in some given interval. Okay.